Hi guys, my name is João and today I'll present you about multi-level intermediate representation. We first must start addressing the challenge we face with today's compilation pipeline. Today we have many specific architectures such as CPUs, GPUs, and TPUs among others, and each of them demand domain-specific optimizations to better perform when executing code. This type of requirement drives traditional compilers insane because they would struggle to perform it. And in these slides, when I refer to traditional compilers, I mean compilers such as GCC and Clang from LLVM. But what exactly is the pipeline of a traditional compiler? We start with the source code, for example in this case C or C++. Then we have a front end, where the compiler will check the source code for syntactic and semantic errors. It receives as input the source code and outputs an intermediate representation. This IR in this case would be LLVM IR. Using it, we can run the optimizations that is through the LLVM passes. At the end, we can generate machine code for x86, ARM, or any other you may want. Our bottleneck here is that using only one level of IR, it is not sufficient to apply all the optimizations we need. We go from a high-level representation, the source code, to a low-level IR, losing abstraction too abruptly. MLIR's idea then is to take the single-level IR and turn it into a multi-level approach. We call it dialects, where each level will progressively lower the level of the representation, enabling more complex manipulation of the code. As an example, we have torch. Instead of going directly to a low-level IR, it starts with the torch dialect, a direct representation from torch operations, but in this case in MLIR. It allows compiler level optimizations such as node fusion and loop optimizations. Then we lower from it to Linalg dialect, which is very useful for scheduling kernels and vectorization. It goes over for many steps, and today in MLIR Torch we have around 8 levels of IR. The rest goes just as it went with the traditional compilers, with them lowered to LLVM IR and generate code for the target architecture. Through MLIR-based compilers, we are able to create more modularity. That means that each dialect can be internally modified without impacting other dialects, considering, of course, that the intermodules API aren't modified. We also achieve more performance. That's because hardware-focused optimizations can extract maximum performance from the target hardware. It also brings more hardware adaptability. We can target a wider range of hardware architectures. And finally, extensibility. We can add and remove dialects and therefore optimizations based on the need of the architecture we target to. There are many projects that use MLIR as its basis. We can name here PyTorch, TensorFlow, and XLA. Those are all ML frameworks that leverage the benefits of MLIR. Now we can go over an example. We start with a simple C code, a function that adds two vectors and stores the result in a third one. We can actually rewrite it in Linalg. Linalg is a MLIR dialect, and in it we must first define a function that receives two tensors and return another one. And we do that because Linalg only operates over tensors. We can then define an operation and what will be the inputs and outputs of it. And then a block of computation. In this block, we must sum both tensors and yield the result, which will be stored in C. Finally, you can just return the resulting tensor. This same code can be represented in SCF, a lower level dialect, where we interpret the tensors as memory reference. We first must define a for of the size of the arrays, and for each position we must load the reference from memory, sum, and store them back to memory. At the end, we just return an empty value, since the computations are through references. And that's all for today. Thank you for your time. Here are the references I use for these slides and also my contact. Thank you.